Hello everyone! In this video we will continue to examine topic 5.4, the magnetic effects of electric currents, and in particular we will begin to discuss the motion of charges in magnetic fields. Alright, so now that we've defined sort of the force, the magnetic force on a moving charge, we can begin to ask the following question, which is how do charges in magnetic fields move? What is the consequence of the magnetic force law? Okay. So let's assume first that a charge is moving in a magnetic field and that the magnetic field is perpendicular to the velocity of the charge. So in that case, if we apply the right-hand rule to our charge, this is our charge right here, our charge is moving in the magnetic field, it feels a force up, what happens a short time later? Well, this charge, unlike the wire, isn't just going to continue on in this direction. It feels this force upwards, and so it moves just a little bit up, okay? But now its velocity is no longer to the right. Its velocity is now in this direction. And so if you put your thumb in the direction of the velocity of the charge and your index finger points in the direction of the magnetic field, then you get a new direction for the force, like so. And as you continue all the way around, okay, you come to the conclusion that the charge, in this case, which is never speeding up, never slowing down, always accelerating, with a magnetic force that is always perpendicular to its velocity at any point, gives one particular type of motion that we've seen before. This is uniform circular motion. So the fact that that magnetic force is the only force acting on the charge and that it is always perpendicular to the velocity of that charge gives exactly uniform circular motion. It never speeds up or slows down, is always accelerating towards the middle. So how do we describe this? Okay, how do we describe this? We describe this by saying, well, the magnetic force is the force on the particle, and it provides the centripetal force. Remember that centripetal force is an idea which refers to what the net force on a particle has to be for it to move in a circle. The centripetal force is not an extra force. So in this case, the magnetic force is the only force acting on our moving particle, QVB. Notice theta is equal to 90 degrees. And that must equal mv squared over r if it's moving in a circle. As a result, you can then solve this equation for r, so you can rearrange it algebraically, and you get that the radius of that uniform circular motion is related to the other variables. In particular, if the mass of the particle increases, that radius will increase. If the velocity of the particle increases, that radius will increase. If the charge of the particle increases, the radius will decrease. And if the magnetic field increases, the radius will decrease. So these two qualities will pull the motion of that charge moving in a circle into a tighter circle. These two qualities, the mass and the velocity, will increase the circle traversed by this particular charge. Notice then that we can use this particular fact and derive a relationship between the period of that circular motion and other variables. Before I do that, though, I just want to point out this particular derivation, both conceptually and mathematically, you should be very comfortable with. This is a set of marking points that exist on virtually every free response question that asks about this phenomenon. So you should be very comfortable explaining how to get this particular equation via a derivation. And that includes the explanation that the magnetic force is providing the centripetal force. So you want to get the vocabulary right. In any case, if we know that the period of that circular motion is equal to 2 pi r divided by v, then you can plug in our expression for r here into that equation, and that gives you an expression for the period equal to 2 pi m divided by qb. And that's fascinating because it is independent of the velocity of the particle. The period of revolution of this charged particle in this magnetic field is independent of the velocity of the particle. And this is incredibly important for devices called particle accelerators. So what this means is that you can speed the particle up, right, and have it come back to the same point in the same amount of time, all other things being equal. So this is super important practical application. You should be familiar with how to get this equation for the radius of a charge moving in uniform circular motion in a magnetic field, and you should be comfortable also deriving this period equation and using it to determine the period of such uniform circular motion.